variability with sampling Mysis. You can have plus or minus 40 or 50%. So we took the averages from each of these points, that's what's plotted, and then calculated the difference using that formula I showed before. And this is the sort of result. Just looking at the data points, I thought, wow, it looks like a sort of negative logistic function, so I fit a curve to it, and it actually looks pretty tight there, so we went with that. And then taking the same model here, and now just, my next step was, okay, so I'm just talking about proportions right now, but I wanted to actually scale it up to sort of absolute numbers. How much across the whole lake, what's it look like on an ecosystem scale? So first off, just again, that same model, just the proportion. This is a map of Lake Ontario, and so given that function here, we're estimating, you can see there's a lot of brown areas here. This would be areas where Mysis that are found in that area would be doing benthic-pelagic DVM, all the ones at that site. And as you move to these deep areas of the lake, you can see we're approaching zero. So those deep areas are kind of two areas where we think it's mostly a pelagic movement. We also know that Mysis biomass tends to increase as you move offshore and then sort of levels off. So this is a lake-wide survey conducted at night where they sampled using cold water column tows all across Lake Ontario in 2013. So same data are on the left and on the right. And so I wanted to fit another function to that to sort of describe how their relationship, just in terms of night pelagic abundance, scales with depth. And so we put another curve with that, and we use that for the next map. So scaling this up to the whole lake estimate, I took the two functions that I just showed you together. And then we took into account Lake Ontario's bathymetry. And the end result is this lake-wide map of Mysis biomass that we estimate is being transported from the benthic zone up into the pelagic area at night through migration. So I'll zoom in on that a little bit. Now you can see it's a little bit different than that just proportional graph where we now have a ring of blue that surrounds, I should mention I excluded, I think the cutoff here was like 20 or 30 meters depth. So that's why you have a ring of white around first, just because it's too shallow for Mysis generally. But so this area of blue around the edge is first defined because, well, there's not really much Mysis biomass there, but those animals that are there would be doing benthic-pelagic DVM. And then really the hot spots are these sort of rings that occur at intermediate depths. And it's much wider here just because of the way that the slope is a lot shallower. And of course, where my office is over here in Oswego, we're fortunate that we have a really steep depth gradient which allows us to access some of this deep water. You can see just how tight this narrow band is. And this is in terms of dry biomass, milligrams per square meter. But it also highlights these two areas where, despite there being a lot of biomass offshore, we don't really think that they're coming actually from the bottom. So that ecosystem service of benthic-pelagic coupling seems to be mostly in these intermediate depths. So then another way of sort of summarizing this analysis or these data, wanted to sort of quantify on, given Lake Ontario's bathymetry and the results shown here, just how much biomass on a whole lake scale is transported at different bins. So the top panel here is the surface area of Lake Ontario by different depth strata. You can see we're sort of limited in the amount of area that has these very deep depths, and then we have a lot of sort of depths or a lot of area in these intermediate depth ranges. But on just a lake-wide basis, so the bottom graph here is the amount that was transported to the pelagic habitat from the modeling exercise. And on a lake-wide basis, when we sum these all up, it's about 6,000 metric tons of Mysis that I'm estimating DVM from benthic to pelagic habitat. So another way to put that in perspective, that's about 4,400 Honda Civic equivalents. So I also have another number that I forgot to throw in here, but we're talking about trillions of individuals out there. I know the number for Lake Superior, I think the estimate is like about 9 trillion individuals. Lake Ontario is a smaller lake, but it's still somewhere in the trillion. And like I said, most of that, in this case, this is what kind of surprised me, is about 57% of that amount is just occurring between 100 and 160 meters. Whereas only 14% of that is occurring at depths greater than 160 meters. And you might be thinking, all right, well, you're just talking about, using, like, there's that saying, correlation is not causation, or in this case, I'm just using observational data. There's no mechanism behind it. But I just want to provide this other slide of, this is comparing different body sizes of the animals. So the lower part here, this is our 110 meter site, 130 up to 200 meter site. This is an example from June. And to me, this is also some pretty striking evidence that we seem to be sampling the same group of individuals, say at 200 meters day and night. The reason why you're having two dark bars here is that there's this adult cohort and then also a juvenile cohort. And at shallow depths, the only ones we're able to find in the water column are these juveniles. They seem to have a higher tolerance for light levels compared to adults. But when you get out to the 200 meter site, there's almost no separation between the two peaks. So the body size distribution is almost identical. Oh, there's a text for it. So to sum up with some take-home messages from this work, it's still kind of ongoing. I'm playing around with different ideas for some of the depth functions, but we identified a couple different zones, mainly those two offshore areas where the Mysis population seems to display different migratory behavior. Mainly they're just migrating from deep to pelagic areas, deep to shallow pelagic areas. And the extent of Mysis DVM is likely controlled by preferred light levels rather than this need to be benthic. We've often put them in the box of they're always going to migrate down because they just got some advantage there, but it seems like maybe this there's another alternative hypothesis for what's driving DVM in the present, and that's this isolume hypothesis, just meaning that they prefer to be in some sort of preferred light level, albeit much lower than what you and I can tolerate. And the other part that sort of jumped out at us through this work is the influence of lake morphometry on ecosystem-wide estimates of flux. So Lake Ontario is shaped one way, if another lake is shaped a different way with much deeper area and a lot less shallow area. That's going to affect your estimates for this type of exercise as well. And if you're curious about any of this stuff, there's a ton more work coming. We have a cross-lake study that is being led by Rosie Chapina et al. Should be hopefully in prep sometime this spring. And that basically did a sort of similar sampling design to what I just shared here, but lakes including the Canadian experimental lakes, other Great Lakes as well, I think Michigan, Superior, Lake Champlain, even Finland and Denmark, where they have a similar species that occupy similar roles. And that's it. This is not from this year. There's no ice stuff. Jim?
So Brian, migrations they can be energy intensive, and the reason for doing it is a trade-off between what you get and what you have to burn up to do it, right?
Yeah.
So do you think in the deep case, it's just not worth the effort to go all the way to the bottom because they don't get enough out of doing it?